Okay, we're going to talk now about vector components and the projection of one vector onto another. So I'm going to kind of revisit this idea that I was talking about in the last video of, or this situation where we've got two vectors that are, in an angle between them. So here we just two random vectors, u and v. Now in the last video we discussed this idea of the shadow of one vector onto another. So well, let me do it like this. I was describing sort of, if you imagine, this is the way I picture it at least, but if you imagine sort of a light source here shining light down perpendicular to the vector v. Okay. Then vector u sort of casts a shadow onto vector v. And I'm going to make that shadow here blue. Okay. Okay. And that also actually creates another vector. I guess I'll make it sort of pinkish here. And we didn't really discuss that much before, but in the previous one, but we'll talk about it a bit now. And let's actually name these vectors. This one, we'll call this one W1 and the pink one W2. Okay, and W1 was what on the previous video was what I was calling the shadow of vector u onto vector v. Okay, but you can see here that if I thinking about how vectors add, W1 plus W2 equals vector u. I'm going to write that down here. I'll write it up here. Okay, and in a sense what we've done is we've broken down vector u into two component vectors. One component, W1, is going in the same direction as v. The other component, W2, is going in a perpendicular or orthogonal direction. Okay, and what I was saying in the previous video was that a dot product is really just multiplying this the length of this W1 times the length of V. That's how you can think about it. Okay, but what we're going to do now is not find the length of the projection as we were doing in the previous video, but to talk about how we would actually find out what W1 is. In other words, how could I write its vector components if I'm given vector v. Vector v, by the way, has components v1, v2. I want to write the components for vector w1. And the way we're going to do this, just to give you an idea, is we're going to take vector v and we're going to find a unit vector going in the same direction as vector v. And if you remember how to do that, I'm not going to use u because I was already using u. I'll just write the vector. I'll just write unit vector. A unit vector going in the same direction as v would be vector v divided by its own magnitude. If you remember that formula from block day. Okay, well, we're going to take this unit vector going in the same direction as v that would have a magnitude of 1, and we're going to multiply by the magnitude of w1. And then it would have the magnitude of w1, but going in the direction of v, and so therefore it would be the vector w1. That's what we want. Now we were calling this x, this length x, in the previous video, and we saw that the length, if we're trying to find the magnitude of this w1, we saw before it was the magnitude of u times cosine theta. There's theta. Magnitude of u is just the hypotenuse of this triangle. And you can do some trigonometry to see that this length here, the blue length, would be the magnitude of u times cosine of the angle. Now, this, we're actually going to replace. We're going to write that in a, I could just say this times the unit vector, and that would give me vector W1. But the textbook, for the convenience of the formula, it turns out to be more convenient to write it in a slightly different way. And so I'm going to do just a little bit of algebra here. If we've got u dot v equals magnitude of u, magnitude of v times cosine theta, right? U times cosine theta, I can move this magnitude of v to the denominator of this side. I'm sorry, I can move the magnitude of v, to the denominator of this side. And that would show me that u dot v divided by the magnitude of vector v is the same as magnitude of u cosine theta. So this magnitude of u cosine theta is the exact same thing as u dot v. I didn't mean to draw that. U dot v divided by the magnitude of v. Okay, so here's the idea. We've got the magnitude of our vector W1. We've got its direction, because this is just, it's going in the direction of v. So here we've got our unit vector going in the same direction as v. If we can multiply this, this will be a scalar. It's a length, a magnitude. We can multiply that scalar times this vector, and that'll give us the vector W1, which is what we were trying to find. I know this got sort of abstract, but you can watch the video again if you, if you want to kind of go through it. But so we've got, this is the magnitude of W1, which is u dot v over magnitude of v, and we're multiplying this by v over magnitude of v. And I know this looks kind of crazy, but it all checks out. And we want to write it just slightly prettier. We're going to do this magnitude of v times magnitude of v. That is the magnitude of v squared, which actually, if you remember from earlier in 6.4, turns out to be the dot product of v with itself, but we're just going to write it here as the magnitude of v squared. So it's all that times vector v. So this is just one scalar that we're multiplying times vector v. And what that gives us, again, just in case we forgot, is it gives us vector w1, which is the part of vector u going in the same direction as vector v. And we actually have a special name for that, but I didn't want to give you the name before we did this formula, because I didn't want you to be too intimidated. Obviously the formula looks intimidating, but it's really not that bad. We know how to do a dot product, we know how to do a magnitude, we know how to multiply times a vector. The way that they write this vector w1, they don't call it, I was calling it the shadow of vector u onto vector v, just so you kind of get a sort of conceptualize it. The way they write it, they call it the projection of vector u onto vector v, and they write it like this: projection of vector u, and then in the subscript they tell you what it's projecting onto vector v. So this means the projection of vector u onto vector v, or you can call it w1. And if you go to your notes, that's what all this is about. If you see here, w1 is the projection of vector u onto vector v. They kind of show you here how it breaks down, okay? And they give you this formula that we just derived. So that's all. We just did sort of this third and the beginning of the fourth page, and we have just a little bit left to go here. Okay. Oh, and by the way, if you might say, well, how do we find W2 now? Is it going to be a heck of, as complicated as W1? Well, really, since we know that u equals w1 plus w2. If we know u and we know w1, finding w2 is actually very easy. I'm going to do it down here. w2, the part of u that's not going in the direction of v, it's just u minus w1. So that's actually, the hard part is finding w1. Once we've got that, we can easily get w2. Okay. So let's do an example. Projection of u onto v. Then write u as the sum of two orthogonal vectors. So first, let's find the projection of u onto v. I'm going to draw these two. So 3, -5, and 6, 2. I'm going to give myself a lot of room. I advise you guys to do the same. And really, the grid is not as important here. Like, as long as you got them in the right quadrant, you know, the grid might kind of clutter it up for you. I don't know. I'm going to do it without a grid. So 3, -5 is my u. I'm going to, well, let me do it in different colors here. Let's see. Let's do blue. Okay, so 3, -5, that would be over 3 down 5, so kind of like that maybe. There's my u. And 6, 2 is my v. Maybe do that, I don't know, orange. So 6, 2, that's going to be kind of, that one went over 3, so this has got to go over quite a bit more. Okay. Seems all right. Okay, so what we want to find is the projection of u onto v. Now this might be harder to visualize, but if you kind of imagine our light source kind of shining light perpendicular to v, right? So, or maybe think about it, just go from the tip of vector u and draw perpendicular to v, right? There's our perpendicular. And what you've done when you do that is you've broken down vector u into two components. You've broken it down into, this guy, the part of u that's going in the same direction as vector v. That's what we were calling w1. And then, let's say this guy, which is the part of vector u going in a direction perpendicular to v. This we're calling w2. Okay, so we want to find both w1 and w2. By the way, vector w1 we called, that sort of, the other way to name that is the projection of u onto v. The part of vector u going in the same direction as vector v. Okay. We don't really have to do any more trigonometry or geometry or anything like that in this problem. We can just use the formula that we derived. We kind of earned that, so let's use it. It involves the dot product and the magnitude of v. So let's find those first. So I'm going to find, I'll go ahead and rewrite my formula so I can get kind of familiar with it. Projection of u onto v is dot product of u and v over magnitude of v squared times vector v. All right, well, let's first do the dot product. And these kind of more complicated formulas are good opportunities to practice your basic vector operations like dot products. 3, -5, 6, 2. Dot 6, 2. So that's 3 times 6 plus -5 times 2. That's 18 minus 10, or 8. That's u dot v. Now what about the magnitude of v? That would be square root of 6 squared plus 2 squared. 36 plus 4, I'm just going to leave that square root of 40. I don't need to worry about simplifying it because I'm going to square it anyway up here. So, and then v obviously is 6, 2. Okay, so I'm putting this into my formula. I've got the projection of u onto v, or also w1 in that figure, is 8, the dot product, over square root of 40 squared. Obviously 40, but I'm going to write it like that for now, times vector v, which is 6, 2. And if we simplify here, that's 8 over 40 times 6, 2, which is that 8 over 40 is the same as 1 over 5. Then you multiply that scalar through, so it ends up being 6/5, comma, 2/5. There's our W1. Now if you look up here, it's sort of reasonable. 6/5, go over 6/5, up 2/5. That's our W1, the projection of U onto V. Okay? That's the first part. The second part is easier. Don't worry. That's our W1. What we've just done is we found the projection of U onto V. But then it says write U as the sum of two orthogonal vectors, two perpendicular vectors. Well, you can see the first vector we already found, W1. Second vector, W2. So we want to find what is W2. Well, remember, W2 is just, since W1 plus W2 is equal to U. I'll go to my pink. W2 is just U minus W1. U is 3, negative 5. So this would be 3. What am I doing? 3, let me start over down here. 3, negative 5, that's U, minus vector W1, which I already found. 6/5, 2/5. 3 minus 6/5, I'm going to go ahead and do this sort of quickly just for the sake of time. 3 is 15/5 minus 6/5, that's 9/5. Negative 5 minus 2/5, negative 5 is negative 25/5 minus 2/5, that's negative 27/5. There's our W2. Right? So then I can write vector U, which, by the way, is 3, negative 5. I can write it as the sum of two orthogonal vectors. I can write it as 6/5, 2/5. I should really go back and color code this, but it's been long enough already. Oh, okay. That's my W1, 6/5, 2/5, plus my W2, which is 9/5, negative 27/5. And you can go back, you can confirm, number one, that when you add W1 and W2, you get vector U. And you can also confirm that W1 and W2 are orthogonal. You can do their dot product. And if you do, you'll see their dot product is 0 because they are perpendicular. Okay, this is the end of part 3. When you're ready, move on to part 4.